Alright, Bismillahirrahmanirrahim, Assalamu alaikum. So I've already been discussing with you the concept of sources of magnetic fields. So a current is the source of magnetic field, and we've already seen the Amperes law. The Amperes law basically states that if I have a loop, a closed loop of any shape whatsoever, and if I take the magnetic field on each point of this loop B, whatever the direction of the magnetic field is, and if I'm traversing this loop in a clockwise fashion, that is in this fashion, I can break up this path into small infinitesimal trajectories dl. What I could then do is take the dot product of the local magnetic field with the path dl and integrate over the closed path. So this is a line integral that I can always form, and this line integral must equal the current that pierces the surface on whose outer perimeter lies this path. So if there is current that is coming out, and I denote this by a dot, which means the current is coming out of this path. Here I have another current element coming out. Here I have a current that's going inside this path, say I3. Then this line integral must equal I1 plus I2 minus I3, etc. So this is Amperes law. And I assign positive signs to this I1 because if I have my thumb pointing in the direction of this current, then, I've made a mistake here. I'm traversing this in the anti-clockwise fashion. So my dl is pointed like this, and I'm traversing this path like this. Sorry about that. So I'm traversing this path in an anti-clockwise fashion. I form this integral. This integral equals plus I1 plus I2 minus I3, and I assign a positive sign to those currents which are coming out of the plane of the blackboard. And how do I know that? I have my thumb pointing in the direction of the current, then my fingers are curled in the direction of the trajectory along which I am traversing this path. So this gives a positive contribution, and this gives a negative contribution. So this is Amperes law. Alright, now we've already seen Amperes law. Let's look at a few applications of Amperes law. And we all know that it doesn't matter what kind of path this is. It could be a nice circular path, it could be a tortuous path, it could be a serendipitous path, any kind of path. But it has to be closed. Such as in the Gauss's law, you have to use a closed surface. Alright, now let's look at a solenoid. And consider an infinitely long solenoid. Ali, I need some chalk, some colored chalk. पीला खास तौर पे Now, what is a solenoid? A solenoid is basically a coil of wire, and I assume it's infinitely long and it's really thin. So if I were to draw this coil of wire in 3D, it would look something like this. what this coil will actually look like. However, if I were to draw a longitudinal section of this wire, current is flowing through this coil in a particular direction. If I were to draw a longitudinal section, this is what I would draw. I have a current that's coming out from the top and going in from the bottom. Then there's the next coil of wire. Then there's the next one. And so on. And being a finite mortal being, I have drawn some spacing between these coils, but I assume that these are tightly packed together. And the length of this solenoid is infinite, and it's a really thin coil. It's a thin solenoid, so it's a slender, long solenoid. And what I'm interested in finding is the field inside this solenoid, the magnetic field. And I would like to invoke Gauss's law to find out that field. Don't have enough jaw. All right. Now, if I look at one of these coils, the magnetic field is pointing towards the right. For the next coil, the magnetic field is also pointing towards the right. So all these magnetic field lines are continuous. And if this is an infinitely long solenoid, the magnetic field at this point is going to be the same as the magnetic field at this point. And the magnetic field here is going to be the same as the magnetic field here. Because this point sees an infinite stretch of currents coming out, and it sees an infinite stretch of currents coming in. And there's no difference between what an observer here would see and what an observer here would see. So all of these points are totally equivalent if this were really an infinitely long solenoid. This means that the magnetic field inside is going to be uniform, and it's always going to point towards the right. So the magnetic field inside the solenoid is assumed to be uniform. B is the magnitude of that magnetic field, and it's uniform. And since it's an infinitely long solenoid, the magnetic field cannot actually come out of the solenoid. It's always trapped inside the solenoid. Only if we were to truncate the solenoid would these field lines come out. Such a field is called a fringe field. So the fringe field only exists at the ends of the solenoid, but it's an infinitely long solenoid anyway. So if I were to draw an Amperian path, let's draw an Amperian path. Remember, now I have to draw paths. Paths are one-dimensional objects. Surfaces are two-dimensional objects. Gaussian surfaces exist in 3D and they are two-dimensional surfaces. But a path is really just a circuit, a loop. So I draw a loop, and the loop that I would like to choose is something like this. And I traverse this loop in an anti-clockwise fashion. And the length of this loop that I've chosen is small l. Now I would like to use Amperes law. If I were to use Sabieh law in calculating the magnetic field inside the solenoid, it will be a huge, complicated labyrinth. The algebra will be too messy. So I would like to use the simple form of Amperes law. So when I'm traversing the loop towards the right, the magnetic field and the direction of traversal are the same. So the dot product of the local field and the direction of the traversal is positive. So in this section I have a contribution BL. Here the magnetic field is parallel to the axis, but the traversal is normal. So the contribution is 0. Here the contribution is also 0. Here there is no magnetic field. So around this path, the line integral is simply BL. But this must equal mu naught times the total current that pierces the surface. And which surface am I talking about? I'm talking about the surface inside this loop. So I have an I current that's coming out here, an I current that's coming out here, because all of these coils are actually in series. The same current is winding down the helical solenoid. So it's the same current that's coming out of all of these coils. And how many coils are there? If I have n coils per unit length, the total length is L, so the total number of coils inside this section is NL, and the current is I. So NLI is the total current that pierces this surface, and I can simply see that this L just washes away. It's good because L was a construct of our imagination. This Amperian path doesn't really exist. We transported this Amperian path because we would like to apply Amperes law, but in reality there is no such Amperian path that physically exists. So L just drops out, which is fortuitous, which is good. So the magnetic field inside turns out to be mu naught Ni. So this is the magnetic field inside a long slender solenoid. And if you would like to put vector signs, and if you take this to be your y direction, then the magnetic field is a vector mu naught Ni pointing in the j direction. And don't confuse this with the current density, by the way. So this is the magnetic field due to a solenoid, inside the solenoid. Outside the solenoid, it's zero anyway. Let's look at another example. Let's look at the example of a toroid. If I just take a solenoid and wind it on itself and make it into a donut, it becomes a toroid. So a toroid looks like this. It's a solenoid that has been wound on itself. The two ends of the solenoid have just been connected together. And now there is current that is going around in this toroid. Current coming out, going in, coming out, going in. Notice that the coils on the outer periphery of this toroid are slightly further apart because it's at a greater distance from the origin of the toroid. So current is coming out, for example, going in, coming out, going in, coming out, going in, coming out, going in, and so on. Now if I would like to find the magnetic field inside, the magnetic field is going to be trapped totally inside this toroid. It's not going to leak out, because there is no fringe field. There is no possibility for the magnetic field to come out. So if the current is wound in this direction, the magnetic field is actually like this. It's circulating in this direction. So now I've drawn the magnetic field, instead of an arrow, I've drawn it by flux line. I've connected the arrows and I've drawn streamlines. So this is also an alternative depiction of vector fields, as we all know. So now if I were to draw the Amperian path, of course the Amperian path which I choose is now coincident with the point at which I would like to find out the magnetic field. So I would like to find out the magnetic field at a distance r, which is inside the toroid, the distance r from the origin. So the magnetic field is always tangential. My path is also circular. So along the path, the magnetic field and the direction in which I am circumambulating this Amperian path, both of them are tangential. But I would like to go around the path in an anti-clockwise fashion. This is the convention. So on each point of this Amperian path, the magnetic field is pointing in the clockwise direction when I am traversing in the anti-clockwise direction. So the dot product is negative. So I have B at a distance r. Right? This is B at a distance r multiplied by dot dl. I multiply this with dl and then I integrate, so I get 2 pi r, but I also get a minus sign because the dot product here is negative, and this must equal mu naught, the total number of turns inside the toroid. Let's call it capital N. Okay, so this small n is the density of turns, number of turns per unit length. This capital N is the total number of turns. Now what is the current that is piercing? Look at this current. This current is going into the plane of the black hole. Right? So if I draw an Amperian path, if I draw this Amperian path and I take this area, I would like to look at the current that is piercing this area. So each one of these coils carries a current I because the coils are all bound in series. Okay? So if this is the direction of the current that's going inside, so the fingers of the right hand would point in the clockwise direction, but I am going in the anti-clockwise direction. So all of these will give a negative contribution. So I will put a minus I here. Hence the the magnetic field at any distance point, there is no concept of total magnetic field by the way. The magnetic field at any of these points along the circular path, which is denoted by B as a function of R, turns out to be equal to mu naught capital N over 2 pi R. BR 2 pi R mu naught N I. Alright, and this is tangential. So this is the magnetic field inside a toroid, and it depends upon R by the way here. It does depend upon R. This capital N is a constant. If I am towards the inner periphery, the magnetic field is larger. If I am towards the outer periphery, the magnetic field is smaller. Inside the toroid, inside this annular region, the magnetic field is 0. Outside the toroid, the magnetic field is 0. So now we have used Amperes law to find out the field inside the toroid. Alright? Yes. अगर देखो ये मेरा path है, if this is my path, and if I am moving around the path in an anti-clockwise fashion, currents that are coming out have a positive contribution. Currents that are going in have a negative contribution. Alright? So this is my second example of the application of Amperes law. Now I would like to look at a scenario in which Amperes law is difficult to apply. Consider current carrying loop, a single loop of current. Now here I have many terms. By the way, a toroid is a technologically important device because it is used in the tokamak fusion reactor, in which a strong magnetic field makes a plasma inside this material and it makes the plasma go around, and it's used for creating the fusion reaction. Alright, now consider a single current carrying loop. For example, if I were to draw a real world sketch of this current carrying loop, it would look like this. I have a ring of wire, not a ring of fire, but a ring of wire that is carrying a current I, and it's a circular ring, radius capital R. Now I would like to find out the magnetic field that this circular loop produces. Now it's a single loop. Right? Now Ampere's law is always valid, just as Gauss's law is always valid. But whether you can use Ampere's law to your advantage and find out the magnetic field using it, it's another question. Here, you could use Ampere's law to find out the magnetic field because this line integral turned out to be a simple form. The magnetic field was uniform at this distance. Here, the magnetic field is uniform, spatially uniform, homogeneous inside the solenoid. So you could easily compute the dot product and take the line integral. And then you could find out the magnetic field. But that's not always the case. Here, if I were to sketch the magnetic field, if this were the direction of the current, if I were just to attempt at sketching the magnetic field lines and would connect them by straight lines, this is what the magnetic field is going to look like. So along the axis, it's going to be normal to the coil, and away from the axis, it's going to turn like this, This is what the field lines will look like. Right here, the field lines will actually turn around and come back here. These field lines have to turn around and come back here. These field lines have to turn around and come back here. These field lines have to turn around and come back here. So this is the pattern of the magnetic field. Of course, it's a non-uniform field. It's an inhomogeneous field. It varies from point P to Q to R to S. So the field here is going to be different, here it's going to be different, here it's going to be different. Everywhere it's going to be different. It's a non-uniform field. Now it's impossible to come up with, or really difficult to come up with an Amperian path unless you're using a computer and you could do simulations. But it's really difficult to come up with an Amperian path and find out the local dot products and then integrate. It's really hard to do that. So even though Amperes law is valid, you cannot use it to your rescue. You cannot use it to your advantage. So in this particular case, you would like to stick to Biot-Savart law. Remember, in this case, if I were to draw, in any case, if I were to draw a closed surface, a surface that is closed. Now this is not a path, rather it's a surface. So I'm shading this surface. And it's a closed surface, like the kind of surfaces you draw in Gauss's law. So it's a closed surface. Now there are field lines coming into this surface and there are field lines going out of this surface. Now the total number of field lines coming in, all of them have to go out of the surface. For Gauss's law, you have a closed surface. Suppose there are no charges inside this surface. So electric field lines that come in go out, and all of them that come in have to go out. However, if you have the same surface, but inside you have some charge, say plus Q, then there will be field lines going out of this surface. Overall. Alright? So the net flux to this surface is non-zero and it's given by Gauss's law because there is charge inside this surface, inside the volume that is enclosed by this surface. So charges act as sources of electric field lines. Negative charges act as sinks of field lines. So field lines would come in and they would just end on a negative charge. So there will be field lines coming in but not going out. Here there are field lines going out but not coming in. So charges, positive charges and negative charges can act as sources and sinks of electric field lines. But you don't have any magnetic charges. There is no such thing as a single isolated magnetic pole. You have a magnet with a so-called north pole and a south pole. Remember, this is a naive depiction of a magnet. A magnet isn't really like this. You break this magnet. There's a north pole and a so-called south pole here, a north pole and a so-called south pole here. You keep on breaking this magnet. It's impossible to get an isolated north pole or an isolated south pole. Magnetic monopoles don't exist. The equivalents of charges don't exist in the magnetic realm. So magnetic monopoles don't exist. Monopoles don't exist in the magnetic realm. Since magnetic monopoles don't exist, you have this closed surface inside a magnetic field. The field lines coming in, all of them have to go out. So the flux that comes in has to go out. And the net flux to this surface is always zero. Whether there is a magnetic field or there isn't a magnetic field. You take a volume of space and you enclose it with a surface, the field line to this surface, the magnetic field line will always be zero. And this is Gauss's law for magnetism, which simply states that B dotted with dA over a closed surface must be equal to zero. Because magnetic monopoles don't exist. Unless there are some experiments that verify that magnetic monopoles indeed exist, would this law break down? So this is Gauss's law for magnetism, one of Maxwell's 4 equations. And I've already mentioned this in passing. However, let's come back to this problem of the current carrying loop. Now, once again, I would like to draw a longitudinal section of this loop. So, let me draw something like this. So, current flows through this loop in this direction. It has a radius capital R, and I am interested in finding out the magnetic field due to this loop. However, I would like to make my life simpler, and I am only interested in finding the magnetic field at a point which is at a distance y0 from the center of this loop and along the axis of the loop. So I'm going to find out the magnetic field along the axis of this current carrying loop. That's all. So I want to find the magnetic field here at point P. Now first of all, what would I like to do? I want to find the field at a local point. I cannot use Amperes law because the field is so complicated. I cannot draw a path along which the line integral can be easily computed. So I would like to use Biot-Savart law. Now if I were to use Biot-Savart law, I would have to break this current carrying wire into small sections. And I will have to find out the contribution due to each of these small sections. Now let's take a section here. So current is going into the plane of the blackboard here. So current is pointed in here. It's going in. This distance is R, capital R. This distance is R squared plus Y0 squared under root. Okay. Now I would like to find out the magnetic field due to just this small section. Suppose this section has a length dl, right? Now let's first find out the direction of the magnetic field. Now if my I is pointing in, I, dl, which means dl is pointing out of the plane of the blackboard like this, and my r is, this is my unit vector r, I, dl. So my magnetic field is pointing in the upward direction. Now how do I know that? dl is a vector that is going into the plane of the blackboard. R is a vector that is in this direction. So if I were to draw a plane, so this is a plane, slanted plane like this. R is inside this plane and dl is also inside this plane. So dl is into the plane. R is in this direction. This is dl. This is R. So the magnetic field has to be normal to this plane. Alright, that's the property of the vector product. So the magnetic field is pointing in this direction. So I cannot draw a 3-dimensional because this board is 2-dimensional. So what is happening here, just visualize this. The current is inside the loop. It's going like this. The current at the top is going into the plane of the blackboard. I have a point over there. My current is going in. My R is downward. The current is coming out because the current is circulating like this. The current is coming out like this. So the current is coming out. This is the direction of I. This is my direction of R. So I take IDL. I cross it with R. This is the direction of the magnetic field. So the magnetic field is pointing in the general upward direction. Do you get this? Sorry? DL is outward. So DL crossed R is upwards. Alright? So I draw a plane and the magnetic field is normal to this plane. So what I've drawn here is a plane like this. This is my plane. My dl is outward. My r is like this. So dl cross r is a magnetic field that goes like this. Alright? So this is the magnetic field dB due to this small section. Alright? Now let's take a point here. Now here the current is going into the plane of the blackboard. Now what I could do, I could draw this diagram again. And focus on this point. Here the current is going into the plane of the blackboard. This is the direction of my R. So now I could draw a plane that is like this. So in this plane, the dm is going into the plane of the blackboard. Is going into the plane of the blackboard. R is pointed like this. So I take dl cross r, I get a magnetic field that is pointing downwards. So in this case, the magnetic field is pointing in this direction. This is my dB. So if you look at this dB and you look at this dB, one is pointing up, the other is pointing downwards. So their vertical components are going to cancel out. And then horizontal components along the y-axis, they're going to survive, they're going to add up constructively. So if I take this angle to be theta, this angle is theta, this angle would be theta, so only the y components are going to survive. So I take the y component of this field. So my magnetic field along the y direction due to either this section or this section is going to be dBy, is just going to be dB cosine of theta. I'm not concerned about the component along the z-axis because this component is, there's a component here, but this component is anti-parallel to this component. So these components will just cancel out one another. So I have dB cosine theta here. Now I've only taken 2 points on side on this loop, but there are many points on the loop. There are an infinite number of small sections into which I can break this loop. So now the effect of all of these sections will be totally equivalent. What I will get at this point is actually a cone of magnetic fields. So if I look at this point and I look at this point and I look at any 2 points that are diametrically opposite, the magnetic field is going to open up its arms like a cone. So if I were to draw the magnetic field at this point, at point P, the field will actually look like, so these are the 2 vectors that I've already drawn, but due to other sections, the field lines are going to look like this. In effect, I will actually get a cone with a certain opening angle. And there will be field lines along this cone. And only the y component of all of these magnetic field lines is going to survive. All other components are going to cancel out. So I'm only concerned with the y component of the magnetic field, dBy. I can understand it's difficult to visualize this, but I hope I've tried to make things slightly clearer. So this dBy is dB cosine theta. But what is dB? I can use Biot-Savart law. Mu naught over 4 pi I dl crossed with the unit vector r, which has unit magnitude. And now I would like to find out the angle between dl and the unit vector. So what's the angle between the dl and the unit vector? No matter wherever you are on this loop. What's the angle between dl and the unit vector? Up or down? 90 degrees. Everywhere on this loop, the angle between the dl, the direction of the current, and the unit vector is always 90 degrees. Here it's 90 degrees. dl is coming out. So in this plane, dl is coming out and r is inside the plane. The mutual angle is 90 degrees. So IDL crossed with R sine of 90 degrees is just 1 divided by this distance squared, which is R squared plus Y naught squared into cosine theta. Now if this angle is theta, this angle is 90 minus theta, this angle is theta. So cosine theta will be capital R over this. So I put a capital R here over this, makes this go to 3 by 2. This means that this is my magnetic field due to a small section of the wire. Now if I would like to find out the total magnetic field at point P due to all of the current carrying infinitesimal elements, I will have to integrate over dl. But dl is simply r d phi, right? Where phi is some opening angle here. So if this is my small dl, I can define an angle d phi here. So this length is simply r times d phi. Hence, this equals mu naught I capital R. dl becomes r d phi. So this becomes r square d phi divided by 4 pi r square plus y naught squared by 2. And if I were to find out the total magnetic field Py, I will just integrate over 2 d phi, I will get 2 pi. So I will get mu naught 2 pi r squared I over 4 pi r squared plus y naught squared 3 by 2. And if I were to put a vector sign on this, this is of course pointing in the j direction. So this is the magnetic field at a distance y naught, which is pointing along the y direction due to current carrying loop, and it's along the axis. Now if my point y naught was really far away from the loop, or my loop was really small, which means that my y naught is much larger than r, I can simplify this further. And when I simplify this further, what I get, let's look at the magnitude Py equals mu naught over 4 pi 2 pi r squared I. This thing becomes, I take y naught squared as common, I get a y naught cube 1 plus r squared over y naught squared 3 by 2. Alright? This is just the binomial. This is exact. And then I can apply the binomial expansion. This becomes mu naught over 4 pi 2 pi r squared I over y naught cube into 1 plus r squared over y naught squared 3 by 2 minus 3 by 2. Now if this is really small, and I would not like to keep this term because this is really small, r is much smaller than y naught, so r square over y naught square is even smaller than 1. R square is even smaller than y naught square. So I can ignore this term. If I ignore this term, I get an approximation. I just ignore this term, I get mu naught over 4 pi r squared I. This 4 pi, I can make this into 2 pi. I'm not cancelling out this pi for a certain reason, divided by y naught cube. Is this familiar to anything else that you've seen in the context of electric fields? The electric field due to a dipole. the electric field due to a dipole, if you had a dipole like this, it's a negative charge, a positive charge, and you're really far away from this dipole at a distance y0 from the center of this dipole. And if this y0 was really large as compared to this s, then the electric field here, E, was given by 1 over epsilon naught 2 pi the electric dipole moment P over y0 cube. So this is the electric field due to a dipole. P is simply Q times S. We define the electric dipole moment. Now in this particular case, what we observe here is instead of epsilon naught, I have a 1 over mu naught in the inverse position. And I have a 2 pi, I have a y0 cube. Again, I could see an inverse cube dependence on the distance from this current carrying loop. So if this were y0, my magnetic field is going to drop sharply in an inverse cube fashion. This is my V. And I observe in the numerator something that's quite interesting. I have a current and I multiplied this with the area that is inside this loop. So the current is going in a loop, the current is I, and the area of the loop is pi r squared. So this quantity I into pi r squared is called the magnetic moment. So I replace this pi r squared into I with the symbol of the magnetic moment, which is mu itself. So don't confuse this mu with this mu naught. Alright? So the magnetic field due to a current carrying loop is mu naught over 2 pi mu, which is the magnetic moment of this current carrying loop, divided by y0 cube. And if you were to put a vector sign, this is a vector and this is a vector. What kind of vector is this? If I have a current carrying loop, okay, of some cross-sectional area A, capital A, and current is flowing in this direction, I, then my magnetic moment is IA, but magnetic moment is a vector. So the direction of this vector is given by the thumb when the fingers curl in the direction of the current. So the area vector is pointing in this direction. The unit vector, right, which is normal to the plane, is pointing in this direction. So this is the direction of the magnetic moment. So if the current were traveling like this, then the magnetic moment is going to point like this. If this is where our current carrying loop and current was going around like this, right, then the magnetic moment is going to point in this direction, mu. So a current carrying loop is a magnetic dipole, and it produces a magnetic field like this, A bar magnet, a so-called bar magnet, NS, produces a magnetic field that is just like a current carrying loop to an approximation. So it produces a magnetic field like this. And it exists, the field exists inside this magnet as well, because field lines have to be continuous. You cannot truncate magnetic field lines all on their own because there are no magnetic monopoles. So the field lines go like this. So this bar magnet acts like a giant dipole. The Earth itself has a giant magnetic moment. It acts like a dipole. This is the magnetic moment of the Earth. This is the magnetic north pole, the magnetic south pole. For a bar magnet, this is the magnetic moment. So this bar magnet is really a dipole which has a magnetic moment. This is a magnetic moment. The Earth is a big magnetic dipole. A current carrying loop is a dipole, and so on. So we found out the magnetic field due to current carrying loops, and we've estimated that if you're far away from the axis, if you're far away, then you'll get a relationship that depends inversely with the cube of the distance from the current carrying loop. The magnetic fields at other points that are off axis is going to be complicated. Now, if you were to use Amperes law in such a situation, you'll be confounded, you'll be dumbfounded, you'll be really difficult to come up with an Amperian path which you can easily and tractably solve for the magnetic field. Now, we've seen the magnetic field due to a magnetic dipole, we've seen that current carrying loops are magnetic dipoles. Now, what about the electron inside an atom? Suppose you have an electron inside the Bohr atom. Is that electron that is orbiting the atom in a naive picture? In the Bohr's model, it's actually orbiting around the nucleus, though not in the quantum picture. In the Bohr's model, the electron is going around the nucleus in a certain Bohr radius. Now, is that circulating electron, which is really a current, does it produce a magnetic moment? Yes, it does. So, if I have the nucleus here, and I have an electron that goes around the nucleus in a radius r. Now, the charge on this electron is minus e. So this is minus e. Suppose the electron is going around like this, in this direction. Now alright, first of all, let's find out the current. The current is minus e times, divided by the time period, which is 2 pi r v. This is the current due to this orbiting electron. Now this is the current. The magnetic moment due to this orbiting electron is going to be this current times the area of this loop, which is pi r squared. So this is minus e pi r v over 2 pi. This pi goes away, I get minus e m v over 2. Oh sorry, r v over 2. This is the magnetic moment. Now, if the electron is going around like this, the conventional current is going around like this, so the magnetic moment of this electron is actually pointing, of this orbiting electron is actually pointing downwards. This is the direction of the magnetic moment of this circulating electron, which is really a magnetic dipole, by the way. It could be tiny, but it's a magnetic dipole. So, this is the magnetic moment. Now, if I were to make a trick here, if I were to multiply with this with the mass of the electron, I need to divide this with the mass of the electron. Now what is mvr? It's the mechanical momentum of the angular momentum of the electron. That's mvr. So I can put this equal to minus e over 2m L. Alright? Where L is the angular momentum of the electron, the mechanical angular momentum of the electron. So the electron is going around in a circle, it's orbiting, it has a mechanical momentum, and that circulating charge gives you a magnetic moment. So that's quite interesting. A circulating charge gives you a magnetic moment because it has mechanical momentum. So the mechanical degree of motion is coupled with the magnetic degree of motion. Alright? So I can actually make this turn into a vectorial equation by writing something like this. Mu is a magnetic moment, it's a vector, it's minus e over 2m L. Now, because L is also a vector. Now this is Bohr's model. Bohr's model also states, or the Schrodinger picture states, that this is quantized. L is quantized. If this is quantized, then the magnetic moment is also quantized. If you had a proton circulating, orbiting around something, that mechanical motion of a proton will also give you a magnetic moment. So a circulating electron or a circulating proton would also give you a magnetic moment. But the point is that in the hydrogen atom, the first electron in its ground state is in the s orbital. In the s orbital, what's the angular momentum? क्या होता है s orbital में L की क्या वैल्यू होती है? 0. So in the s orbital, the ground state, the hydrogen electron should not have any magnetic moment, but the electron does have a magnetic moment, because in addition to this L, there is some intrinsic angular momentum which is called the spin of the electron, S, which gives rise to a magnetic moment. And this is not the orbital motion of the electron, this is the quantum mechanical property called the spin. And you have a similar relationship. You multiply this with E over 2m and put some constant with it. This is called the Landé G factor. And you get the magnetic moment of an electron due to its spin. So this is the magnetic moment due to its spin. This is the magnetic moment due to its orbital motion. So an electron which is in the s orbital will still have some magnetic moment because of its spin. And this is how spin was actually discovered through 1932 Stern-Gerlach experiment. Now I would not like to go into the details of the Stern-Gerlach experiment or the concept of spin, but I've given you at least some motivation. Now what I would like to talk about is, if you have a dipole, like a magnetic moment, a circulating charge, remember, neutrons, what is the charge on a neutron? 0. So it's an uncharged particle. So one would assume that it would not have a magnetic moment. But since a neutron has spin, it also has a magnetic moment. So uncharged particles can have magnetic moments as well because of their spin. And this is a totally quantum mechanical phenomenon. Alright? It's beyond the scope of this course. Alright, now before I move on to the demonstration, don't be distracted by that because Ali is preparing something. Thoda sa aage chale, I'll answer your question at the end. What I would like to talk about now, what kind of force or torque acts on a dipole. Now a dipole is placed inside a magnetic field, but I haven't talked about forces that act on conductors. So let me first do that, and then I'll move on to the demonstration. Okay, I'll take one question. Yes. Magnetic G. ठीक है, उसमें प्रोटॉन का, उसमें इस डिफाइन करने के लिए प्रोटॉन का चार्ज ले लेंगे और ये न्यूट्रॉन का मास ले लेंगे. Okay? Now what I would like to talk about, suppose I have a conductor, or suppose I have a simple charge, Q. Now this charge is placed inside a magnetic field that is somehow produced by some other moving charges. Alright? We've seen sources of magnetic fields. Now we've assumed that magnetic fields have been synthesized, and I place a charge inside this magnetic field. Now this charge is moving with a velocity v. It's a vector. And the magnetic field is pointing in some direction b. Now I would like to posit or present that there's a force that's going to act on this moving charge. Now remember, this charge is moving, but the observer who's measuring the force is static. The observer is at rest. If the observer is also moving with the velocity v alongside the charge, then the velocity the observer sees is 0. So it's a difficult concept. So when I talk about relativity, I'm going to explain this paradox. So now the observer is at rest and it sees a charge that is moving inside a magnetic field with velocity v. There is a Lorentz force that acts on this charge. And that force, in the absence of any electric fields, is given by Q V crossed with B. Alright? You take the cross product. So here V is pointing like this, B is pointing like this, so the force is pointing outwards. So this charge will be, as it moves towards the right, it will be deflected outwards in the presence of this magnetic field. And if this magnetic field is always there, it will start spiraling or moving in a circular orbit, and I'm going to talk about that. Anyway, this is the Lorentz force. And if on top of this I also impress an electric field in some direction, then there will be an additional contribution due to the electric field. So this is the Lorentz, the mechanical force that acts on the object, and this will cause the charge to accelerate, just according to the classical equations of motion. Now if I have a conductor, a long conductor that is carrying a current I. Remember, current is not a vector, but I'm showing it as a vector, and this is really the current density's direction. Suppose this current is uniform and steady, and this conductor is placed inside a magnetic field. Suppose that magnetic field is pointing into the plane of the black hole everywhere. Right? Inside, pointing into the plane of the black hole, right? Now, I take a small section inside this wire. Of length dl. The force, there must be some force that acts on this section because the charges are moving with a drift velocity Vd. So if I would like to find out the force on this small section, it's dF. According to this prescription, I have the charge on a current carrying a carrier Q, or the charge on an electron, times the total number of electrons inside this section, capital N, into V, which is the drift velocity, because that's the effective motion of the sea of electrons, into B, magnetic field, which is uniform, and the angle between the drift velocity and the field is 90. So sine of 90 is 1. Right? Now, this capital N, you already know, is number of charge carriers per unit volume into A dl, where A is the cross section of this wire. This is A into B, alright, into Vd, into Q. But this Q times N times A into Vd is simply, what is this? This is J. This is J into A, which is I. This is a current. This is IDL. IDLB. So the force on this small section, dF, which is really a vector, is given by I dl, which is now a vector, assumes the role of a vector which is pointing in the direction of the current, crossed with B. So this is the force on a small section of a current carrying conductor. And if this current carrying conductor is really long, there will be a force on each one of these small sections. Now how do I produce such a magnetic field? I can produce this magnetic field by a neighboring current carrying conductor. And this is the demo that I would like to show. But let's first look at the math here. Current carrying conductors. In the economy of time, I've written CCC. Now I have a current carrying conductor that is carrying a current I1, and I have another current carrying conductor that is carrying a current I2. And these are thin conductors, and the distance between them is small d. Now this current inside this conductor will produce a magnetic field. Now that magnetic field at the location of this conductor is going to point into the plane of the black hole. It's going to point inwards. How much is that magnetic field? If this were thin, then that magnetic field can easily be found by Amperes law. That magnetic field B is mu naught times this current. So my Amperes path is now circular like this. Mu naught, the current that comes out is I, and I have 2 pi into D here, that comes here, 2 pi D. So this is the magnetic field here, B, here. Now I have moving charges inside the magnetic field that have been produced by a neighboring current carrying conductor. Now I would like to find out the force on this current carrying conductor. These are infinitely long wires, by the way. So the force on a force on the total length of this wire, F, is going to be given by, look over there, IDL cross B. The current through this wire is I2. dl integrated gives me L. I bring this length here. So I want to find out the force per unit length on this conductor. I2. Now I would like to find out the magnetic field at this point. The magnetic field is mu naught I1 I2 over 2 pi d. Now if I have, suppose I have a 4 ampere current flowing through each of these wires, and the current is moving in the same direction. Let's find out the direction of this force. This force I, dl cross b, the force is pointing upwards. This is the force on the second conductor due to the field produced by the first conductor. If I were to do it reciprocally, the force on this conductor is going to point in the downward direction, minus F. So these wires should ideally attract. But how large is this force? So if I have 2 current carrying conductors carrying current in the same direction, these wires should actually try to come towards one another mechanically. But how large is this force? It's a miserly, meaninglessly minuscule force, really small. 4 ampere, take this to be say 1 centimeter. This is 4 pi into 10 raised to minus 7. I get, what do I get? 2, 4, 8, 32. About 32 into 10 raised to minus 5 newtons. Or 3.2 into 10 to the minus 4 newtons. It's 320 micronewtons. You can find out the weight of an object. You can find out the mass of an object which corresponds to 320 micronewtons. Right? It's 32 milligrams. It's really small. Alright. So, however, what I've tried to do here in this particular demonstration is, let's see if this works. It's a really small effect. So, it's really difficult to see. And we really need to, so what I've done, I've tried to push this to the extreme. I've tried to pass a large current through these wires, through a power supply, and I would like to see these wires slightly come towards one another. Because these wires have mass, they have weight. So their acceleration is going to be really small. These are long wires. So the force is there, but the acceleration might be really small. So what I'm going to try to show you now is whether these wires would actually come together. Alright, it's going to be a really small effect. Tinily small. So let's see if it works. By the way, where's the attendance sheet? Okay. Alright, let's see. Ali, where? Kither focus kar rahe ho? Usi jagah pe. I turn on the power supply. So I'm passing 8 amperes through this circuit, which means 4 amperes in each wire. And if you observe carefully enough, when I turn on this current, the wires at this location, here, they're going to slightly come closer to one another. Just slightly, just feebly. It's a really small effect. I've gone at lengths to actually make this effect observable. So, alright, I'm turning on the current. Here. The current is on, the wires have gone slightly towards one another. I turn off the current, the wires separate. So I turn them on again. Go. The wires are slightly closer together. So the distance between these wires, I would say, is roughly 1 millimeter, because I'm zooming in with the camera. I turn off the current, the wires separate. I turn it on, the wires slightly nudge towards one another. And they can, so here, the current is on, off. Turn on the current again. Let me try to ramp up the current slightly. I'll just try to do it for a short period of time because these wires will heat up. So experiments are not easy, by the way. So, alright. Here you go. So the current is about 8.38 amperes. Slightly increasing the current. It's now 10 amperes. Turn it off. On. Off. Alright. So now what I've demonstrated is that two wires that are carrying current in the same direction will be attracted. Like currents attract, opposite currents will repel one another. In the next class, on Tuesday, I'm going to show you some other demonstrations of how electron beams can be deflected inside an oscilloscope using a magnetic field. So do come to tomorrow's recitation. We're going to do some questions from the tutorials because I don't think you've been attending tutorials this week. And the midterms, I'm not really satisfied with your midterms. You need to do your homeworks properly. Please submit the next homework in time, which I've extended upon your request. Please do hand in the homework in time. Thank you very much and see you on Tuesday, inshallah.